Okay, so now we're going to be talking about implicit differentiation, but I want to go back a little bit to where we did Leibniz notation way back a few weeks ago when we talked about the difference between Lagrange and Leibniz notation and how that was going to be important. Well, it's going to become more important right now. Implicit differentiation is the reason why Leibniz's notation is so important. So just a quick review of what it actually means in Leibniz notation on there. Mainly, it is talking about that we have we're talking about the derivative, and the derivative is the slope of the tangent line, and we're talking about the slope is the rate of change. So we know that the slope is the change in y over the change in x. So we were talking about maybe building a snowball, and as the snowball got bigger, what if we knew the radius of the snowball, we also knew what the volume was, what the diameter was, what the surface area, the circumference, all that stuff we know, because if we know what the radius is, we know all that other stuff. But as it's growing, we also know the rate of change. So if we know the rate of change at which the radius is growing, we know the rate of change as the diameter or the circumference or any of those. If we know one, we know the other. So when we're talking about this, that's what this means. This means that when we're talking about the change in y, oh man, that when we're talking about the change in y over the change in x, that's what is happening. So we could say that it's going to be the change in the circumference as the radius is changing. So I know the radius, that's in the denominator, and I need to know how the circumference is changing. So here, for example, this here could be the change in the height as time is changing. So we know how time is reacting, and then we also know how we know how time is changing. We also know how the height is changing. So this is the fixed one. The denominator, the time is the fixed. H is the one that we now need to know what's changing. So if I were to say the change in the velocity, v, with respect to time, time is the one that we already know, and we're talking about respect to time. And if you guys remember, it was going to be dv over dt. So the velocity is changing with respect to time. This one here is the volume. So we would say dv over dr. We know the radius with respect to the radius. We know the radius, and we want to find out how the volume is changing. And then here we know the perimeter. We want to know how the area is changing. So we say that that's going to be dA over dP. So this is the one, if you notice, this one here is the one that we know, that's the one we're doing it with respect to, and then we are trying to find the area. Okay, so implicit differentiation, here's the warm-up that you were supposed to do. And so if we look at it, and you could pause the video right now and do these so then see if you got them right. So now what you could do here is, this is easy. What we're saying is that it's dx, and then this is dy. So we're taking the derivative with respect to x, and we want to know how y is changing. So this is going to be, when I do this right here, that one would give you the dy dx. So dy is changing with dx on here. And then this one here is, well, this is an x there. So we are just going to take the straight derivative the way we know it. And so that is just going to be 2x. Now here, we're doing it with respect to theta. This is nothing different here. The notation here is the same thing here. That's the equation here. And now we are taking the change in y, because this here is the same thing, equals to y. So the derivative of y of that, we're taking the derivative, and y is equal to theta squared. That's what that's saying there. And so we know that that's going to be the same thing there, and it is going to be 2 theta, because we're taking it with respect to theta. Here we're taking it with respect to x. There's an x. We're taking the derivative with respect to theta. That is a theta, so we do the normal derivative. Here is the same thing. Now here we have, we're taking the derivative of this function, and it's y is equal to t squared. So that's why we have the y is changing with respect to time. It's a t, so we just say 2t. So it's nothing different than what we've been doing before. That is no notation. So now what you want to do is pause the video again and see, can you do these? Can you do them? So if you can, awesome. If you can't, and you're like, well, aren't they the same? They're not. And so when we do this, what we're going to get is that we're going to take the derivative here. Now this is saying that y is equal to y squared. So because notice how this is the y there, that's this y right there. So let me show you, this y right here is this y right there, not this one not this one over here. That's not that y. Okay, so what are we going to do to take the derivative of it? And so the way that we're going to take the derivative of it is, well, we're taking it with respect to x, but there is no x's over there. So how do we take the derivative? Well, it's actually the chain rule. I know you guys love the chain rule. So it's actually the chain rule there. So let's see, how are we going to use the chain rule to actually do this? And so the chain rule says that we have to do the outside function first, and the outside function is actually the square. So the chain rule is actually the square, and the inside is your y. So you're taking the derivative of the outside, leaving the inside alone, and then chaining in the inside. So you're going to take the derivative of the outside, which is going to be your 2, and then you're leaving the inside. You're subtracting 1 from it, bringing that down. And so then we get the 2, and you leave the inside alone. But you still have to take and chain on the derivative of the inside. But when I take the derivative of y, which is this one, I get dy dx. And so that's where we get the dy dx. Now, if that didn't make sense, hopefully you could rewind it and it'll make more sense again. So derivative of y by itself, the inside, is the same as taking the derivative of that, and that's where you get the dy dx there. Okay, so let's try it with this one here. Again, notice how we're taking the derivative with respect to x, not theta, not like we did up here. Not like we did over here where we had, see, that's theta and that's theta. That is not the same thing over here. So what you need to do is take the derivative here again. So again, we notice that this was going to be y equals to theta squared. So the y gives you the dy dx, because anytime you take the derivative of y, it's how y is changing as with respect to x, as x is changing. So anytime you have y, it's always going to be written like that, or any other variable, you're going to have to write it that way as well. So how do I solve this? Well, I know it's the chain rule again. I take the derivative of the outside, and so I know I'm going to get 2, and then I have to leave the inside. Again, if you need to write it, it looks like this. So the derivative of the outside is 2. We leave the inside alone, which is theta, and then I have to take the derivative of the inside. Well, it's what we talked about earlier with the Leibniz here. This is how it's changing. So how is this changing? We are changing theta, so it's going to be the way theta is changing with respect to x right there, and that is your derivative there. So your answers are just going to be that. So your answers, if you look at that, that is it's solved right now. And we're going to talk a little bit more about how we have to get rid of the d theta dx. That's not supposed to be in your answer, but right now, baby steps. Okay, let's look at this one here. You could pause it and try it yourself and then see what happens. Okay, so now what you're going to do, again, here is what we have. We have that, I'm just going to do it here. It's going to be that y, it's going to be that y is equal to t squared. So here we have our dy dx, and then I have to take the derivative of that. Again, t squared, we take the chain rule. The derivative of the outside is 2. The derivative of the inside, well, we leave the inside alone, so it's 2t, and then we are going to chain on the derivative of the inside, so it's how t is changing as x is changing. So it's dt, t is changing with respect to x, and that is your answer. And so that is your warm-up. Okay, very good.